So this is 9,3 beta. Now, this is the distinction you have to make. The link between a two-sided test and a confidence interval for a mean says you could go directly to the confidence interval. The two match up exactly. For a proportion, they don't match up because the proportion test is centered about the null, p sub 0, and the confidence interval is centered about p hat. Now, you would never get a question, I can't see you ever getting a question in May where the answers would conflict for proportion. So I wouldn't worry about it. But in a mean, they can't conflict. So you got a 95% confidence interval from you. If the null's not in there, you can reject mu if it's a two-sided test of the alpha level is 5%. Because what does this mean? 95% is in the center. The alpha level, 5% is the sum of the tails. These two have to add up to 100%. So if it's a 98, if it's a 90% confidence interval, that would correspond to an alpha level of 10%. So in a 95% confidence interval, if the null's not in there, then it necessarily has to be in the tail of the distribution. And if it's in the tail of the distribution, we reject the null. If it's inside the confidence interval, we F2R. Fail to reject. Now, this only works for a two-sided test. You can make it work for a one-sided test, but it's a little confusing and you're not ready to do that yet. And in fact, I wouldn't recommend you ever doing it. It'll work. But you have to imagine that all the alpha levels in one tail. So you'd have to take that alpha level off the confidence interval to make them align, and that might be confusing to think about without me drawing it on the board. So we went back to this pineapple problem, chapter 8. This is what's going to happen in a few years. Well, more than a few, but when I retire, this is one of the things I'm thinking about doing is becoming a pineapple grower. And what happened? The pineapples were 31 ounces last year. That was the mean weight. And you put in a new watering system. Managers wonder if this change will affect the mean weight. Now, it's a silly question because you didn't put the irrigation system, you didn't pay for that to just change the pineapple weight. You did it to increase it. That's not up to us. This is how it's worded. Will affect the mean weight. Affecting it is telling you it's a two-tailed test. You got a random sample of 50 pineapples. So they're asking you to go through, ready? Go through the template. What's the null and the alternate? What are the conditions? Then the 95% confidence interval is this. So without doing the test, what would we get? So the null is that the true mean is going to be 31, what it was last year. And the alternate is that this watering system is going to affect it. Conditions, SRS of 50 pineapples that was given. It's safe to assume that you are growing more than 500 pineapples or you're not going to make a lot of money. And 50 is a large enough sample size, it's greater than 30, to assume that this is going to be approximately normally distributed. 31 is outside the interval. So we would reject the null. There is convincing evidence that the parameter is not 31. I'm 95% confident the parameter is in here. Can we conclude that the irrigation system caused it? No, it was an observation. You'd have to do an experiment to infer causation, okay? Now, the whole point of doing this, right, when you're collecting data, if you're in, PJAS, everybody's trying to reject the null. There's no glory in F2Ring. You just have to count on people being ethical. Remember, you make a type 2 error. The only way you can make a type 2 error is if you F2R. F2R, you could possibly make a type 2 error. So this is a new term for you. The power of the test. Okay, and this is a AP topic, power of the test. The probability that you make a type 1 error. Type 1 error means what? You rejected the true null. That's your alpha level. And the analogy is this. If I had the standard normal curve drawn on a dartboard, and I threw darts, 100 darts at the dartboard, and I was aiming for the center, and if I missed the curve, I would get a takeover. Out of the 100 darts, I would expect 5 of them to land in the tail by chance alone, even though I was aiming for the center. So the probability of making a type 1 error is the alpha level. So we call the probability of making a type 2 error beta, just to use the Greek alphabet, alpha beta. So the power of the test is the ability of the test to reject, the probability that the test will reject a false null. So here's the example. We're back to these batteries. And you have the mean life of the batteries was 30 hours. And then you got more expensive batteries. You boosted it. They developed new deluxe batteries, okay? So we're going to do a one-tail test. The new batteries are more expensive, though. So the company wants to be convinced that they last longer. The power of the test to detect that mu equals 31 is 0.762. So they're giving you this. You're just asked to interpret it. So it means that's how likely the test is to reject the false null. You're testing this. If mu really is 31, the test has a 76.2% chance of rejecting the null of 30. So in this example, the probability that we rejected the null, given that mu is 31, 76%. What's the probability of making a type 2 error? Well, 1 take away that. So type 2 error is 1 take away the power. And then the type 2 error, I refer to as beta. They didn't even write beta here. Power equals 1 take away the probability of type 2 error, or the other way around. The probability to make a type 2 error is 1, take away the test power. Except this, you saw on Kerry McCann's picture that she had in the chapter 8, that I put in the chapter 8 Canvas folder, that there's an inverse relationship between a type 1 and a type 2 error. So if you give the test more power, then you're just increasing the probability of a type 1 error. So you have to come to a balance. So how could we increase the power? Keeping in mind that we're at risk of committing a type 1 error. We can make the sample size larger. Now think about this. We're looking at the t-score. Whatever test statistic we get, the t-score, and we're going to plot that. So the higher absolute value of the t-score, the farther out you're going to be, the more likely to land in the tail when you reject the null. So if the sample size is larger, remember what this t looks like. It looks like how far you are from the null divided by the standard deviation over root n. So you have that division in the denominator. So it's the same thing as inverting and multiplying root n to the numerator, which would increase your t-score. And if you had a higher t-score, you're closer to the boundary or outside the boundary, the alpha level boundary, and you would reject the null, which just gives you more power. The alpha level's larger. So if you go from a 5% alpha level to a 10% alpha level, there's more area in the tail. It's easier to reject the null. And the null and alternate are farther apart. Well, these two go together, 1 and 3, because the numerator's bigger. And if the numerator's bigger, then the t-score is going to be larger, and you're going to be further from the center of the curve. So we have this scenario. Now, unfortunately, what they're doing is they're going back to a proportion, which is awkward because we're in means here. But in this question, the proportion of people that get side effects from this drug is 10%. So when a new drug, and we're going to test it, the proportion of people that get the side effects is less than 10%. So it says the power of the test to detect that the proportion is 8% using a random sample of 300 patients at an alpha level of 5%. The power is 29%. So which would make the power go up and which would make the power go down? Well, think about this. If the alpha level is 1% instead of 5%, then the body gets wider. The power would go down. It would be harder to get into the tail. If the true proportion 6% gets sick instead of 8%, the numerator is greater. And your t-score would be larger, and it'll be easier to get into the tail. Meaning back to 5%. We're not saying these are cumulative, right? It's 5%. We're not changing the alpha level from the question. And then use a sample size of 200 instead of 300. That would decrease the power. Because when you invert and multiply by the denominator and you multiply the numerator by root n, you'd be multiplying by a smaller value. So the power would go down, up, down. Okay? And then, this is just their opinion. Confidence interval, it doesn't matter. A confidence interval and the test are telling you the same thing. for means. And for proportions, they don't align, but your conclusions are not going to conflict. It's in theory, it's possible, but they're not going to conflict on an AP test. Now, ready? P-hacking is the name for this. P-hacking is when people just run tests until they find something that's significant. It's not ethical. Okay? It means you do the test, you build the template, you come up with the alpha level before you begin. You come up with the null and alternate before you begin. Then you run the test. It happens all the time. People run the test first and then back up and write their alpha level and their hypothesis and pretend they found something. Because there's no glory in F2Ring. So these are the bullet points that we began the lesson with. The conditions. The test statistic is the t-score. The p-value is the probability of getting this t-score you got, or more extreme, further in the tail, and that's why these curves are shaded, by chance alone, which means sampling variability if the null is true. Okay? Perform a significance test, use a confidence interval to make a conclusion. If the data point is inside the confidence interval, you are failing to reject the null. If the statistic is inside the confidence interval, F2R. If it's outside, you reject the null. And then the power, which didn't come up until today. So, confidence intervals are always two-sided, always. The power of the test is 1 subtract the probability of making type 2 error, and then p-hacking is testing until you find what you're looking for, which is shady. All right. So I'm going to pause the video, and you're going to go to these 4 questions. 83, 85, 87, 89. Now we're going to go over 2 of them at a time. That's not what I want. I'm getting nervous now. I meant to stop the pause the recording, not stop share. Showing it to you. The t-score, right, is how far your statistic is from your null divided by the sample standard deviation over root n. But that's the same thing as saying x bar, take away the null over the sample standard deviation times root n over 1. Like when we invert and multiply this thing, right? So the t-score goes up if the numerator is bigger. So making the sample size bigger or making these two further apart makes the t-score go up, which makes the power of the test go up. So 83. If the p-value for a two-tailed test is 6%, and there's 94% in the body, the 95% confidence interval will include the null, because the p-value is greater than the alpha level. 95% confidence interval goes with a 5% alpha level. If the p-value is higher than alpha, you F2R. But a 90% confidence interval goes with a 10% alpha level. And that threshold gets crossed because 6% is higher than an alpha level of 5%, but it's lower than an alpha level of 10%. So it's in the body for a 95% confidence interval with a curve, and it's outside the 90% confidence interval, or it's in the tail when the if there's 5% in each tail. Okay. The potato example. Potato chips. If the true proportion of blemished potatoes is 11%, remember that the cutoff the company decided was 8%, and there's a 76% probability the company will reject the false null and return the shipment. That's what the power of the test means. If the parameter is 11% tested against 8%. And that was on the drawing where we showed you that's how far apart the numerator was. Then you would have a 76.4% chance to land in the tail and reject the null. Okay? So we're going to give you a couple more minutes to go to the last two problems. Okay, so for 87, if you increase the alpha level, it makes it easier to reject the null, increase the power of the test. Now this is a proportion, so it's a z-test, and I have p hat. For some reason, p hat showed up here. When I went back to the other ones, I still couldn't get it to show up on the other PDFs, so sorry. So here's the numerator. As n gets smaller, when you invert and multiply this, the numerator gets smaller. So the z-score would get smaller, and it's harder to get to the tail and reject the null. It would decrease the power of the test. If the numerator up here, 1100 take away 800ths, is wider, is greater than 10 hundredths, and 10 take away 800ths. So if you went from 11 to 10, the power of the test goes down. All right. A higher alpha level increases the probability of a type 1 error. Type 1 error is you rejected the true null. If you go from 5% alpha level to 10% alpha level, there's more room in the tail, and it'll be easy to reject the null. Except the price to be paid, increasing the sample size means it's easy to say, it makes the power go up, but it costs money. Okay?